Hello, in this video I'm going to talk about black bodies and Planck's radiation law, and this is our first step from classical physics into quantum physics. And although I'm going to be talking about these two topics in particular, the black bodies and the radiation law, it's important not to lose sight of the story behind all of this, the point of why this is relevant to this transition from classical physics into quantum physics. So I'm going to put this story, at least the high level parts of the story, right at the beginning of the video, just to make sure we can keep this in mind while going through the details. So what we're looking at here is thermal radiation. So we've got oscillating particles inside some material. So we've got these charged particles that are oscillating around, and if we've got oscillating charged particles, then that means we've got electromagnetic radiation being emitted. So we're looking at this source of electromagnetic radiation, and this is pretty much what we're getting at by talking about black bodies. I mean, I'll get into the details of black bodies a little bit later on, but they're a particular idealized type of object that absorb electromagnetic radiation in a particular way and emit electromagnetic radiation in a particular way. So just think of black bodies at the moment as being our source of thermal radiation that we're then going to study. So based on the radiation that's emitted, the thermal radiation emitted by these black bodies, we can then look at some spectrum coming off of a black body. So this is our intensity against wavelength, much like we had when we were looking at stars. We were approximating stars as black bodies, and you get some kind of profile going on, some kind of spectrum here of intensity against wavelength. And it's okay, well, here is our observation. What is our theory that's actually going to describe and predict this observation? What's underlying this? And we've now got the confrontation here between the old theory, so this is our classical physics, and the new theory, which is the quantum physics. And in the old theory, it was a case of, right, we've got electromagnetic radiation. So that means we've got some waves, and the energy in these waves can take any value up to some maximum. So any value less than or equal to some maximum energy. So we've got this continuous distribution of energy. This is what classical physics says, how it describes waves and therefore the electromagnetic radiation. Right, based on this foundational assumption of classical physics, is it possible to then predict this observation? The answer being no, it isn't. This is what Planck was working on. This is where the radiation law, Planck's radiation law, comes into the story, because Planck was trying to figure this out, and his conclusion was no, classical physics cannot lead us to this observation, so we need something new. And what is new is this quantum physics, and this has got a couple of features to it. So the electromagnetic radiation is, well, yeah, we do have waves, but we've also got particles. We've got this wave particle duality going on here with this electromagnetic radiation. These particles are photons. So that is step one of the new theory, at least the parts that are relevant to this particular topic. And then these photons, furthermore, are quantized, the energy. So we've got quantized energy, meaning that the energy comes in packets of fixed value for a particular frequency of wave. So these are packets of energy. And for a wave of frequency f, the energy of a packet of energy, the energy of a photon, is the Planck constant multiplied by the frequency of the wave. So, Planck got honoured with the naming of this constant after him. If we were going to write this in terms of wavelength rather than frequency, we'd be saying that is hc over lambda, where we've got the speed of light times the Planck constant on the numerator and then the wavelength of the wave on the denominator. And Planck discovered that if he made this assumption instead, that we've got quantized energy in packets in these photons, then yes, this new physics, this quantum physics, would lead us to these observations. So we had a match there between the theory and the observations. So that's why all of this is so important. Right, so with that in mind, let's move on to black bodies then. And as I mentioned, we've come across black bodies already in the astronomy and cosmology section when we were talking about stars, and we were modeling stars as black bodies. And we looked at things like Wien's displacement law and Stefan's law, and these are both concerned with black bodies. They're both concerned with thermal radiation. So just quickly recapping those. So the displacement law, this is when we're looking at the continuous part of the stellar spectrum, although it doesn't have to just apply to stars. We've got our intensity against wavelength. Let's take a hotter star where we've got a very pronounced peak at short wavelength. Then the displacement law is saying, well, the wavelength at which the peak occurs, so this is our lambda max, is inversely proportional to the temperature, or another way of putting it is lambda max multiplied by the temperature is a constant. So as we change the temperature, if we've got this spectrum for a particular temperature T1, if we have a cooler temperature T2, then the peak will move off to a longer wavelength. And if we were going to draw in a dotted line connecting up all of the peaks of all of these different continuous spectra, then this dotted line would have a 1/t shape to it. It's got a reciprocal graph shape. So that was the displacement law. And then we've got Stefan's law, which was telling us about the luminosity. That it's the surface area of the star multiplied by the Stefan-Boltzmann constant multiplied by the temperature to the power of 4. So that's telling us something about the area under the curve. So these two things are already telling us, these two laws here are telling us two things about these black body profiles. The shape, well, not the full shape, but where the peak is in the displacement law, and then something about the area under the curve from Stefan's law. Now, that's obviously not telling us everything because it doesn't tell us the shape. If we want to get a more detailed description of exactly, why is it the shape that it is, then we need more information in this. And that's where Planck comes in a moment. But why is this linking with black bodies? Well, black bodies have a couple of key features. First of all, in terms of absorbing radiation. So if they've got electromagnetic radiation incident on a black body, then a black body will absorb 100% of the electromagnetic radiation that's incident upon it. And that is setting a high bar to say it's 100%. So really, this is an idealized object. It's a theoretical object, but we can get pretty close to reproducing this. We might not get it exactly 100% because that is as extreme as it gets, but we can get very, very close to 100%. So that's one thing with black bodies. They absorb all of the electromagnetic radiation that's incident on them. They're not reflecting anything. The other thing as well is they radiate in a particular way. And the way that they're radiating is meaning that we're getting to look here at thermal radiation. And it means we can create a relatively simple experimental setup. And we can create a black body in the lab, which is fairly easy to understand in how it's constructed, which makes it easier to then try and explain it. We've got fewer moving parts, essentially. We can say, right, let's take our theories of physics and then predict how this setup, this experimental setup, will behave, and then see if that matches the observations. So that's why black bodies are so useful for this, because they give us our source of thermal radiation in a relatively simple setup that we can then try to explain. So how do we create a black body then? The usual one that gets drawn out is we get this box with a small hole in one side. So we create this box completely sealed except for the small hole. And on the inside, it's all matte black. So it's matte, so it's not reflecting. It's black, so it's absorbing as much radiation as possible. So we've got this matte black interior. If we've got any radiation that's coming in, because remember, this has got to absorb 100% of the electromagnetic radiation if it's going to be a black body. So you get some radiation come in, and it's going to collide. We're going to get a reflection, although hopefully not much of one, off of one of the walls. So the incoming radiation through the hole, incident on the wall, vast majority of it is going to get absorbed on the first impact, the first meeting with the wall. We're going to get most of the radiation is going to be absorbed. Some of it gets reflected, then we're going to hit the wall again, and we're going to get another high percentage gets absorbed. And it's going to keep bouncing around in this box, because the chances of it coming back and hitting the small hole and going back out again is pretty low because it's a small hole. So if it does come back, if the path leads us back to the small hole, it would have had enough collisions with the walls that pretty much 100% of the radiation would have been absorbed. And this is why you get a slight modification on the pictures to the oblong shape of the box. So put a little ridge at the far end here. This is just a ridge on the wall of the box, because of course if you get a ray coming in normal to the hole, normal to the back surface, it will just go in, hit the back of the box and bounce out again. So it'd just be a one impact, a one reflection route in and out. So we put a little ridge there to stop that from happening. So this is getting 100% or near as 100% as we can get of the radiation being absorbed. So the actual black body is the hole in the box, because that's where anything that's incident on the hole, any radiation incident on that gap here, that hole in the box, is absorbed. We're not saying that the black body is the surface of the inside of the box, because that's not absorbing 100%. We need multiple reflections for as good as 100% to be absorbed. So the black body is the actual hole in the box. That's where we're getting 100% absorption. What goes in doesn't come out. Right, once we've set that up, we can then look at the emission properties of a black body. And if you've got a black body in thermal equilibrium, then it will radiate thermal equilibrium. Then it is going to radiate in a particular way out of that hole. We're just going to get thermal radiation coming back out of the hole. So anything that's going in is absorbed, but the inside of the box, all of the walls of the box, they're all going to be vibrating around. We've got those oscillating particles. They're emitting thermal radiation, and some of that is going to come out of the hole. So we're going to get some radiation coming out. Most of it is going to be bouncing around on the inside of the box and getting reabsorbed, which is helping to keep everything in thermal equilibrium. But most of the thermal radiation isn't coming out of the hole, but a small percentage will come out. So if we can then focus that into a beam and then disperse it through a prism, then we can look at the spectrum of the thermal radiation which is coming out of that black body. That is what we need to try and explain with our theories. And this is where Planck came in. Well, a lot of people came in. Planck was the one who figured it out in the end. But you had a lot of people trying to figure this out. We'd create something like this in the lab, and people were creating these. I mean, the one of the first notable ones, it was a spherical copper object that was heated up. So you had this copper sphere with the small hole, blacken all the inside of the copper sphere, heat it up, keep it at a constant temperature, and then we've got thermal radiation coming out of the hole. So this is what people were looking at. So the path then to Planck's radiation law is people were looking at this thermal radiation spectrum that was coming out of this black body. They were seeing something that was looking like this. You've got a peak on there, and people were trying to match the theory with the observation. So famously, you had the Rayleigh-Jeans law for this, where they had some kind of success matching this. but it was limited. So they were using classical physics, and they were saying, right, what we've got here is the walls of the inside of that copper sphere. These are harmonic oscillators, essentially. So we've got a whole load of atoms jiggling around in harmonic motion, and they are emitting photons. And the waves that are coming out, well, they were thinking of it in terms of waves rather than photons. So yeah, a wave approach rather than a particle approach. But you've got electromagnetic waves coming out of these oscillators. And they were assuming, as I said at the start of the video, that these oscillators could emit energy up to any maximum value. So you had a maximum value, and it could be any value up to that maximum. It was a continuum. And Rayleigh Jeans were taking this approach, and they got a good match for longer wavelengths. But as it got the shorter wavelengths, things just sort of headed off to infinity. They had this big problem at shorter wavelengths, that there was a massive difference between the theory and the observations. This was what was called the ultraviolet catastrophe, because they were so far out. There was such a big problem here. And this was the best that people could come up with, really. I mean, it wasn't just, oh, yeah, we're close to it, we just need to tweak something. It was just way off. There was no one close at all. So then Planck came on the scene in 1900, and Max Planck, he made the assumption that the energy came out in these packets, that it was all quantized, and if you treated the energy in these quantized packets, then you could get an exact fit with the observations. And he came up with the Planck radiation law. Now, there's a lot of different ways of writing this down, and you don't need to know this. I'm just trying to illustrate the complexity of the law. So the energy at a particular wavelength that's emitted by one of these black bodies, 2 pi times the Planck constant multiplied by the speed of light squared, divided by the 5th power of the wavelength. And then we get this really horrible looking exponential. So e to the hc over lambda kt. So we now got the Boltzmann constant that's turned up as well. And you can see we've now got the temperature here. So this is showing how this spectrum is going to vary with temperature. -1, take the reciprocal of it. So it's a complicated equation. This is way beyond the maths that we're able to deal with in pre-university physics. But I'm just illustrating, this is what it is. It's a complicated formulation. Planck managed to come up with this idea that we've got quantized energy. Now, that doesn't mean to say that he actually thought that this is necessarily the reality of how these waves were behaving. There's some suggestion that really this was just a mathematical trick he saw himself as using in order to get the answer. There needed to be more investigations in order to see what this actually meant. What was the implications of having to make this assumption. And this is what was then happening over the next 10, 20, 30 years, that people were dealing with the implications of this. We'll see this in the next video when I go through the photoelectric effect. But Planck had shown that this was at least a path to a solution. And now he, along with other scientists, were trying to figure out what that actually meant in terms of physics in general. But yeah, he managed to come up with this. And of course, the next thing is working out what Planck's constant is, because we've got this new constant has appeared here, which we've already seen in the quantization of the energy of these photons. A simple relationship here between energy and frequency of these waves. And we've got this Planck constant that he managed to get named after himself. So we need to know what Planck constant is. And it's a very small number. This is the smallest of our constants. So 6.626 or 6.63, depending on how accurately you want to use it. I mean, it goes to more decimal places. Times 10 to the minus 34. And we can see what the units are from this simple equation here. So we're going to have joules second, because we've got energy divided by frequency. So joules divided by 1/seconds. So we've got joule seconds for the Planck constant. So how will we go about actually getting a value of Planck's constant if we were in the lab? Well, the way that comes up in textbooks quite a lot, and sometimes you get exam questions on this, is using LEDs. Now, this wasn't available to people back in the day, you know, Planck was doing this in 1900. The first LED was created in the 1920s, and they weren't really in common use until the 60s, 70s, 80s. So LEDs weren't around at this particular time. But if we set up a circuit with an LED, so let's have our we'll have our power supply here, and we'll have a variable resistor. So whack a variable resistor in, then we can put in our LED. So we'll put a resistor to protect the LED a little bit, because you know what LEDs are like for blowing up. And put our LED in here. I'm having to squeeze this in a little bit because I haven't got much space at the bottom of the page. So we can have that. Stick a voltmeter around the LED, and then have a fly lead then going off to this variable resistor. So as we move the fly lead around, we're going to be getting a different potential difference across the resistor, depending on how we're changing this parallel branch here. So this is allowing us to change the voltage across the LED, and we want to find the threshold voltage, because remember with LEDs, you know, we've got a semiconductor here, and semiconductors and then these LEDs in particular are working by, you've got electrons and you've got electron holes. So these are spaces in the structure of the semiconductor that electrons can sort of slot into if you can move them across the depletion zone of the semiconductor. Yeah, we went through all this in the circuits videos. So if we can combine these, get a recombination of an electron and a hole, then we will get a photon emitted. So this is a one-to-one interaction here, electron into hole, so one recombination, one photon comes out. So if we can put a blackout screen around the LED, crank up the voltage until we get first emission, then that first emission is going to be telling us the energy that we're going to have in these photons. So we've got the voltage, our threshold voltage. So if we multiply voltage by charge, so the charge on the electron, that's giving us the energy that we put in to the electron. So that's what we're getting released when we get this recombination. That is then going to be equal to our photon, our HF, or our HC over lambda, whatever way we want to look at it. Usually people go with a wavelength approach on this. You know, the LEDs, they often tell you, I mean, I know you can work out the frequency easy enough, but they'll tell you the frequency or the wavelength that the LED is set up for. Okay, it might not be the narrowest of narrow bands of emission in the electromagnetic spectrum, but it's, you know, it's going to be a color. You have a red LED, they'll tell you what the wavelength of the emitted light is. So we know the wavelength, we know the speed of light, we've measured the threshold voltage, and we know the charge on the electron. So we can then plot something out here. You know, we can plot out, if we're saying that the voltage that we're measuring is HC over lambda E, we can plot voltage against 1 over wavelength for multiple LEDs. So we repeat this a lot of times. We repeat it for each LED, average the answers, repeat for multiple LEDs, plot this out as voltage versus 1 over wavelength, and then we'll get some kind of scatter, draw in the best fit, and we're going to get the gradient is HC over E. So that's allowing us to work out the Planck constant in a fairly simple experimental setup. So yeah, I mean, the small numbers involved, I mean, this is another thing to mention here. I mean, you can see for this here, the energy that we're looking at, it's a small amount of energy. You know, say it was a volt to get this LED to light up. So 1 volt multiplied by the charge on the electron, that's our energy. So that would be 1.6 times 10 to the minus 19 joules. That's energy, just because we're doing 1 times the charge on the electron. Very, very small amounts of energy. So this is where the idea of an electron volt comes in. So, and oh, I missed out the N. So electron volt. So an E, lowercase e, capital V, EV, unit of energy. So that is this calculation. So an electron volt is accelerating an electron through a potential difference of 1 volt. What energy do we end up with? So 1 volt multiplied by the charge on the electron, 1.6 times 10 to the minus 19 joules. So that is 1 electron volt. And you'll get this as a definition question in exam questions loads. It comes up so much. So don't get mixed up. It's not a unit of potential difference, it's a unit of energy. And if we want to convert from joules to electron volts, we just divide by 1.6 times 10 to the minus 19. So that is the amount of joules that we've got there. So say someone said, oh yeah, we've got 3.2 times 10 to the minus 19 joules. So we divide by 1.6 times 10 to the minus 19, and then we get 2 electron volts. So it's simple enough. It's just getting an easier way to deal with very small quantities of energy. So yeah, that's run through pretty much everything that I want to say about black bodies, Planck radiation law, and how that has led to that transition from classical physics to quantum physics, at least opened the door very firmly for further investigations. I'm just going to leave it with one more comment coming back to stars. We've been modeling stars as black bodies. Why is that okay? Well, remember I said a couple of things about black bodies earlier on. So we want them to be in thermal equilibrium, and we want to have a fairly small percentage of the photons being emitted, of the energy being emitted from this black body. So, not much was coming out of the hole. There wasn't, most of it was staying inside. Some of it came out, and overall it was staying in thermal equilibrium. And this is what we see in stars. You think of, we're looking at the photosphere of a star when we take a stellar spectrum. And in that photosphere, well, the temperature is pretty much constant. They're certainly over the short to medium scale. Stars evolve, but they're not evolving quickly. This is, happening over millions of years, or even longer. So there's a lot of time between any significant change in a star, and you get radiated energy. Obviously that's what's being radiated and we're looking at, but that gets replaced by energy from the core of the star. So in the photosphere is in a fairly decent thermal equilibrium, and also most of the photons in the photosphere are just being scattered around inside the photosphere. They're not just, you haven't got this massive photon dump coming out of the star. They're getting scattered about, absorbed, re-emitted, all manner of things that are going on in the plasma that's there. But it's mostly just scattering of these photons. And then you get a smaller percentage actually get released. So stars are showing that black body behavior, and this is why they are well modeled by a black body profile. And we see this for other objects as well. It's not just stars. They just happen to be the thing that we're looking at in pre-university physics that look black body like. And the Planck radiation law is really, really useful. It's much more detailed and accurate and just insightful than the displacement law. Wien's displacement law, okay, it's there for illustrative purposes to a large extent. It doesn't get used as much as the Planck radiation law. If you really want to pin down the temperature of a black body, your go-to is not going to be the displacement law, I wouldn't have thought. The Planck radiation law is just a much better description of what's actually going on. And as I say, it's got various different formulations that you can use depending on what it is you're trying to do. So there you go. That just sums up everything that's happening there. But this is the way in anyway. This is why this needs to be the first video. This is how quantum physics is getting that door opened. And now I'm going to, in the next video, get onto photoelectric effect, where Einstein was really starting to piece together the actual theory behind this. Why was Planck having so much success with this approach with quantized energy? So on to the next chapter.